morning students. Last class we have finished aluminum compounds. So today we are moving towards carbon elements. So as you all know about carbon, it's found as a native as a graphite, coal, crude oil and carbonate rocks. It's a calcite and magnesite. It contains large quantities of carbon. It's combined with the elements silicons, silica. Silicate minerals are clay and other important compounds of silicons. These are some physical properties of the elements of carbon groups: carbon, silicon, germanium, tin, lead. It's all physical nature are solid, an atomic number, an atomic weight, an electronic configuration, melting point, boiling point details has been given. You just go through this table. So apart from this group, carbon have a special ability as it can form a catenation. Catenation means nothing but forming of chain compounds. So carbon its ability for an element form chain of atoms. So for the following conditions are necessary for catenation. So first condition is valency should be greater than or equal to 2. So carbon is more than 2. So element should have an ability to bond with itself. The self bond must be strong as the other elements. That's a much more important condition. So CC bond should be stronger than CX bond, means other heteroatom. So kinetic inertness of catenated compounds towards other molecules, and carbon possesses all the above properties and form wide range of compounds with other elements. So second main 5 more important 5 more questions is allotropes of carbon. So carbon have many allotropic forms. Out of that, graphite and diamond are most common allotropes. Other important allotropes are graphene and fullerenes and carbon nanotubes. So graphite. So graphite, so well-known examples graphite in pencils. Pencil nib is made up of graphite. So graphite is the most stable allotropic form of carbon at normal temperature and pressure. So it soft conducts electricity. It's composed of flat two-dimensional sheets of carbon atoms. So each sheet has a hexagonal net of sp2 hybridized carbon atom. sp2 means double bond. So bond length is 1.41 angstrom, which is close to the CC double bond. So each carbon atom forms 3 sigma bonds with the neighboring carbon atoms, and 3 of its valence electron and 4th electrons will be unhybridized p orbital. So one fourth electrons will be available for making conjugations, and these pi electrons are delocalized. So this is the responsible for its electrical conductivity. The successive carbon sheets are together weak van der Waals force. That's why its strength is very weak. So van der Waals successive sheet is 3.40 angstrom. Another one is structure of diamond. Unlike graphite, the other allotrope of diamond is very hot. So the carbon atoms in the diamond are sp3 hybridized and bonded to 4 neighboring atoms. So see, difference between graphite and diamond is important. So there sp2 hybridization, carbon is bonded with 3 sigma bond. Here sp3 hybridization, carbon is bonded with 4 near about sigma carbon atoms. So their bond length is 1.41, which is close to double bond. Here the bond length is 1.54, which is single bond. So it's for their hexagonal arrangement, here tetrahedral arrangement. So each carbon atoms that extends to the entire lattice as shown in figure 2.5. So all the valence electrons have been involved in the bonding. So there is no extra electron, additional electron for conjugation or delocalization. So diamond will not conduct electricity. That is the reason why diamond does not conduct electricity. So another one is that recent developments. Fullerenes are newly synthesized allotropes. There are naturally occurring isotopes. Fullerenes are synthesized allotropes of carbon. Unlike graphite and diamond, these allotropes are discrete molecules, concrete molecules. C32, C50, C60, C70, C76. So all are the examples of other type of fullerene compounds. Out of this, C60 is commercially important, which looks like a saucer ball like structure. It's called Buckminster fullerene or buckyball structure. It consists of 26 member ring and 12 5 member ring and completely sp2 hybridized, and it can conduct electricity in form pi bond and free electrons also. So the bond length is close to C double bond C single bond. So carbon nanotubes, this is another discovered allotropes, have graphite like tubes with fullerene ends. So along this axis, these nanotubes are stronger than steel, conduct electricity. So these have a wide variety of applications. So another allotropic form is graphene. This is the graphene. Here also sp2 hybridized and densely packed with the honeycomb crystal structure. See, this is very important 5-mark question, so I don't want to go to further. We just go through this allotropes of carbon carefully. It's a important 5-mark question. So once again, I am giving short notes or key points of each allotropes. So first one is graphite. So graphite is sp2 hybridized. So carbon can form 3 bonds. Now out of 1 electron will be delocalized in sp2 orbital, which is responsible for its electricity conduction, and its bond length is 1.41 and hexagonally close packed. So in case of diamond, say sp3 hybridized, so it has formed 4 bonds, so there will be no availability of extra electron, so it cannot conduct electricity. So the bond length is 1.54 and it's hard in nature. So fluorine is made up of C60, C12, different type of compounds. It's a concrete molecules, and its structure contains 26 member and 12 5-member ring. So sp2 hybridized and bi electron will be there, so it can conduct electricity. So in back to carbon nanotubes, it's another recently developed isotopes, allotropes. So you just go through this question carefully. It's 5 more questions. Thank you.